Hello everyone, I'm Vangelia Anna Marcato, and today Francesca Falzon and I will be presenting our paper, Full Database Reconstruction in 2 Dimensions. This paper is in collaboration with Axima, David Cass, Adam Rivking, Jesse Stern, and Roberto Tomasia. We consider a user that wishes to store their information on the cloud. Commonly, a user would send their plaintext database on the cloud service, and the cloud service would host it. Then the user is able to send queries, like return all records from area A. Since the data is plaintext, the cloud providers can just look through the data and return the results. Now, notably, in case the cloud service is malicious, they have a lot of information. They know everything in the database, it is plaintext, all the queries, and all the responses. Now, if our user is a little bit more security-oriented, they might want to do something like the following. Send an encrypted database to the cloud. Instead of plaintext queries, send query tokens that, along with a private query processing algorithm, enable the cloud provider to look through the encrypted data and return the encrypted results. There's a number of technologies that can achieve this result, but the one we focus on is searchable encryption. Searchable encryption is on the more efficient side, however, they have to sacrifice some security for that. This manifests through leakage. We focus on 2 common types of leakage: access pattern leakage, where the adversary can observe the set of encrypted records in a query response, and search pattern leakage, where the adversary knows if a query has been asked before. In our setting, we consider 2-dimensional databases where points have 2 attributes, and range queries return all points that are inside a given rectangle. We consider a passive persistent adversary that is able to observe communication for a very long time. The adversary creates set RMD, the response multiset of encrypted database D, that contains every possible response that the adversary can observe. Now, using RMD, the adversary wants to extract information about this database D. There have been a number of attack papers in this area, starting with Kilaris et al. In 2016, and up to now. All papers so far have focused on 1-dimensional databases, and we are the first one to look at 2-dimensional ones. Moving on to our contributions, we present the first full database reconstruction attack from leakage of range queries in multiple dimensions. We saw that the solution space, or reconstruction space, contains up to an exponential number of possible databases to the database domain size. Nevertheless, we present an attack that achieves reconstruction in near optimal polynomial time and polynomial space. We support our attacks with experiments on real-world databases, and we also present a symmetry-breaking attack that uses auxiliary information to reduce the size of the reconstruction space. Now first, let's look into the reconstruction space. What does it look like? Well, given a database D, how can we generate an equivalent database D prime? Our first idea was to use the symmetries of the square. So given D, we can rotate it by 90 degrees, rotate it by 180 degrees. And turns out, all these 3 databases are equivalent. Well, but why? Well, given this range query on D, if we rotate it in the same way we rotate the database, we get equivalent queries. But that's not all. If D has the given shape, where there are only points in components S1 and S2, and S2 dominates S1, turns out we can fix S1 and flip S2, or fix S2 and flip S1. And turns out all these databases are equivalent. Okay, but why? Well, given the range query from before, we can generate equivalent range queries by flipping an endpoint of the query if it is in a component that is flipped. All these 3 range queries are equivalent as they contain the same points. And thus, all these 3 databases are equivalent. Now, the worst case scenario is when a single point is in a single component. And thus, we can generate an exponential number of equivalent databases to the original one, D. And now Francesca will tell us about the attack.
Hi, so I'm going to give a quick overview of how the attack works first. So the first thing I want to introduce is the notion of query density. So given a point W in our domain space, we can ask how many unique queries contain this point W? And we can formulate an equation, as you see on the left here, that computes this number. And we can take this equation and we can plot it over the reals to obtain a curve, the curve on the right. Now, just note, however, that we're really only interested in integral solutions because the records we are considering are of integral values. Now, we can generalize this idea to multiple points. So we can ask, similarly, how many unique queries do V and W appear in together? And again, we can write down a similar equation and plot it. And the interesting thing to note is that now we can start looking at the intersections of curves. So before, there were 8 possible integral values for W along the gray curve. But when we look at the intersections of the green and gray curves, we have reduced the solution set for W down to 2, namely W and its reflection across the diagonal. And so we can proceed in this manner until we have reduced the solution set as much as possible. So how do we use these equations? Well, firstly, the idea is to identify the IDs of the leftmost and rightmost records. And we can do this using set operations on the axis pattern leakage. Then, using the equations we saw before, we can compute the possible integral values for L and R. And this value is, these solutions are polynomial in the domain size, and they seed the family of equivalent databases. So once we've found our L and R, we want to partition the remaining IDs into 3 sets, all the records above R, all the IDs of records below L, and then everything in between. So then, given a solution for L and R, we can uniquely solve for the records in the yellow and green regions, and we can solve up to at most 2 solutions for the records in the blue region, namely the record value and its reflection. And the symmetry is what gives rise to the reflectable components we saw earlier. As we go through this process, we just prune any databases that are not consistent with the leakage. And that will give us the full family. So we tested our attack on 3 real-world data sets, Malta Spitz, Chicago crime data, and HCUP hospital data. The picture you see here is taken from the Malta Spitz data. The image on the left is the original data, and the image on the right is the reconstruction. And you can see here the yellow points are the reflections across the diagonal, and the blue boxes denote the reflectable components. So overall, we saw that the vast majority of these databases leaked a family of size 8, namely we reconstructed up to the square symmetries. The largest family was of size 1024, and we noted that multiple components do occur in real data. So lastly, I'm going to touch upon our symmetry breaking attack. So here's the idea. In practice, an attacker might have additional information about the data. For example, it might know the distribution from which these points are coming from or drawn from. So given auxiliary knowledge of the distribution, can we find a database in our family that minimizes the mean squared error? And the answer is yes. In fact, we tested this attack on the same 3 data sets I mentioned earlier, and we saw that this was most effective for the HCUP databases. This attack was slightly less effective for denser databases and databases with many reflectable components, however. So to recap, We presented the first full database reconstruction attack from leakage of range queries in multiple dimensions. We showed that the reconstruction space is exponential, but we were able to reconstruct in polytime and polyspace. We tested our experiments on real-world databases, and we also presented a symmetry breaking attack to reduce the reconstruction space.